Okay, we started recording. Assalamu alaikum. Hello, everyone. Good morning, good afternoon, good evening, wherever you are, and thank you for joining us. I can see there are a lot still joining, and we have already a good amount of attendees and about 300 registered for this webinar. We will be starting with the introduction. I will introduce our host, Dr. Marwan Al-Zailai, and then the main speaker, Dr. or Engineer Mohamad Hussein. So Dr. Marwan Al-Zailai is the Senior Geotechnical Manager at Dubai Development Authority. He is also acting as adjunct faculty in Hirwat University in Dubai and other local universities as well. He is a co-founder for Gulf Geotechnical Engineers and vice president for the Geotechnical Materials and Engineering Committee under the Society of Engineers in UAE. And we have also Dr. Mohamad Hussein, who will deliver the Deep Foundations webinar today. He is the Executive Vice President of GRL Engineers and Executive Director of Global Industry Relations at the Biodynamic. He is the world's oldest and largest specially deep foundations testing services company and testing equipment manufacturing companies. The well-known BDI, of course, if you are involved in geotechnical and biotesting, you will know about it. He has consulted on more than 1,000 deep foundations projects in 35 states in the USA and several countries across the region. He frequently organized educational courses, seminars on deep foundations, including the American Society of Civil Engineers, continuing education classes in deep foundation design, construction, and quality control. He is a member of the Deep Foundations related committees of the DFI, ASTM, BDCA, American Society of Engineers, and TRB as well. He chaired the Deep Foundation Committee of the ASCE Geo Institute between 2002 and 2009, and the BDCA Education Committee from 2012 to 2013, and currently the chairs of the BDCA's technical committee. Mohamad is a recipient of several professional and industry awards and recognitions, published over 60 technical papers, and co-edited 10 engineering books. He has achieved expert level on the BCDA BDI dynamic measurement and analysis proficiency test and on the foundation quality assurance high strain dynamic biotesting examinations. Without any further ado, over to you, Dr. Marwan, if you want to shed the light on the Gulf Geotechnical platforms and the Society of Engineers and any thing else before we hand it over to Engineer Mohamad.
Thank you, Engineer Hamza, for your introduction. First of all, I would like to thank our guest, Engineer Mohamad Hussein, about the topic about the deep foundation types, installation, and testing for the geotechnical load bearing capacity and structural integrity. This event, as you all know, we do it in different timing or series. We have reached up to GeoTalk 5, GeoTalk 8, I mean, and it's between Gulf Geotechnical Engineer platform, which we have it, and we do a lot of this activity through it, as well as through the Society of Engineers, Geotechnical and Material Engineering Committee. I don't want to take much time. I think we have very interesting presentation will be by Engineer Mohamad Hussein, and you can start, Mohamad, and you can start your presentation. Thank you.
Thank you, Dr. Marwan, and thank you, Engineer Hamza, and greeting everybody from an early morning from Orlando, Florida. I wish I was with you in the Gulf area, but hopefully I will see you there soon. I'll try to make the next hour or so interesting and hopefully useful to your practice and as far as deep foundations testing is concerned. So deep foundations are used to support all types of structures and all kinds of geotechnical conditions for a variety of reasons to resist all types of load combinations. They can be divided in a variety of ways. I will divide them today into driven piles, and there is a manual from the United States government that can be downloaded in 3 volumes in PDF format. This manual for the design and construction of driven pile foundations was actually written by engineers from my company, GRL Engineers. And this is a website where it can be downloaded from. At the end of the presentation, I will give you my email address. So if you are interested, please email me. I will send you a link to download this manual. I will also talk about board piles, for which there is also a manual from the United States government you can also download similarly. And I will also mention Auger-Cast in-place deep foundation piles, for which also there is a manual of design and construction. So deep foundation have been used for a long, long time, particularly driven piles, who had been mentioned by the ancient Greek historian Herodotus 2,500 years ago. We now have buildings and structures that are hundreds of years ago founded on foundations, still using the same piles. In today's practice, though, those piles were, by the way, timber piles for thousands of years. In today's practice, driven piles consist of steel piles and concrete piles. And there are literally hundreds of different hammer models that are used to install these driven piles. So we drive piles individually, typically in a pile group, to form a deep foundation to support a bridge pier or a building. During the driving of the pile encounters dynamic pile driving resistance. However, to support a building or a structure, we need to know its static load-bearing capacity. The best way to evaluate a pile's static load-bearing capacity is to perform a static load test, for which we need to pile up dead weight, dead load on top of the pile as a reaction for a hydraulic jack that we put on top of the pile and load it. And then we plot the applied load and corresponding movement of the pile top. So we plot incremental load and corresponding incremental displacement of the pile top. So this is why we perform a static load test, to establish this relationship between pile top loading and pile top movement. It is always advised to also install strain gauges along the length of the pile to perform this static load test in order to establish the forces in the body of the pile under the applied load that will allow us to evaluate the friction resistance and end-bearing capacity of the pile. So although it's the best thing we can do to evaluate static load-bearing capacity, static load testing has limitations. Limitations of cost, it costs a lot of money to do it, and time, it takes a lot of time to perform it. We also have to be mindful of the safety aspect of performing these static load tests, because they involve very, very high loads to perform a test. So let's look at the dynamics of pile driving and try to see if we can use that information in order to evaluate the static load-bearing capacity of the pile. And a very smart engineer called Mr. Edward Smith in Texas, realizing that the dynamics of pile driving is best evaluated by stress wave mechanics, elastic one-dimensional elastic mechanics, wave propagation. He wrote a computer program called Wave Equation Analysis of Pile Driving. This computer program that Mr. Smith wrote in 1948 is often cited as the first application of digital computers in civil engineering. This is the very first computer analysis program in civil engineering, the one that Mr. Smith wrote to analyze the dynamics of pile driving. The United States government commissioned a group in Ohio, our group, the GRL Engineers, a long time ago in the 1970s, to write a wave equation program for public use. This program now, the commercial version of it, is now available from Pile Dynamics by the same authors of the original WEEP program called GRL WEEP. Wave equation analysis is a very powerful simulation program that uses numerical methods in order to evaluate the static load-bearing capacity of the pile based on its driving resistance, which allows the establishment of relationship between pile driving blow count and static load-bearing capacity of the pile, which the inspector can then use as a quality control and quality assurance to make sure that every pile is driven to the required blow count to achieve the required design ultimate capacity. So it's a very powerful simulation program. However, being a simulation program, it requires assumptions in order to constitute the model to be analyzed. Because of the need of these assumptions, then that creates a potential sources of error in the results. Because one would not only would have to be knowledgeable in the different assumptions needed and the different parameters needed to constitute the model, quite frankly, one has to also be a little bit lucky in order to hit on the right assumptions to use. So instead of assumptions and simulation analyses, let's now talk about measurements. Instead of assuming parameters, let's go on the job site and measure what we need to know, analyze these measurements, and come up with the results that we seek. The idea of these measurements was established at Case Western Reserve University in Cleveland, Ohio, in a research program that lasted 12 years, sponsored by the Ohio Department of Transportation, as well as the United States Federal Highway Administration, FHWA, as well as a number of other highway departments. The research program was headed by Professor George Goebel, he's the one standing up in the leads, assisted by students Dr. Frank Raushi and Garen Likens. So during that period of time, not only did they invent the sensors needed for the dynamic measurements under the impact of the hammer, the sensors were invented, the computer to analyze these sensors was also invented, as well as the science and the engineering needed to analyze these measurements, including the formulas and the equations that are required to extract the static load bearing capacity of the pile from the measurements of the dynamic resistance under the hammer blow during pile installations. These measurements and analyses now are used worldwide, utilizing the pile driving analyzer known as PDA and the CapWeb signal matching computer analysis program available from Pile Dynamics. So let's start from the very beginning. This is the static load test. We need all of this dead weight to perform static load testing. We're load testing this pile statically with this dead weight. What if we were to think a little bit differently? What if I was to take a very small portion of this dead weight, very small percentage of it, put it in a guide, lift it up high enough, and drop it in such a way that that will produce the same load on the pile as all of that dead weight? I can engineer that. I can figure out how heavy should the weight be, how high it should be dropped, so I can produce the same force on the pile dynamically as all of that static load test. That is basically the difference between a static load test and a dynamic load test. All I have to do now is use the hammer itself, because the hammer is dynamically loading the pile. The hammer is pushing the pile to the ground, impacting it. So the impacts of the pile driving hammer in the process of pile installations become the loading, the dynamic loading itself. All we have to do now is put some sensors on the pile and take measurements during pile driving. This process had been standardized by ASTM standard D4945. So dynamic load testing, therefore, is nothing but the measurements of load and movement of the pile under the impact of the hammer, and analyzing these measurements utilizing elastic stress wave mechanics. The load is measured with a strain transducer, the one on the left-hand side of the photo, and the motion, the movement of the pile, is measured with an accelerometer shown on the right-hand side of the pile. These are very small instruments, 3 inches in length, about 10 centimeters, that are bolted on to the pile during pile driving. These can be bolted into all types of piles, driven piles, steel, concrete, even timber piles, as well as cast in situ deep foundations, such as board piles. So when the hammer impacts the top of the pile, a stress wave is generated that moves down the pile length. Once the front of that stress wave approaches the sensors locations, which are 1 meter below the pile top, then the sensors see or feel a sudden rise in the force of the pile and the movement of the pile. Then the stress wave goes by, continues on to the bottom of the pile, reflects from the pile end, and comes back, at which time the sensors feel it again. So therefore, the strain gauge and the accelerometer, the sensors on top of the pile, will feel the initial impact of the hammer and the reflection from the pile bottom. This constitutes a test result of one hammer blow. This is a dynamic load test result, a dynamic signature of the pile under the impact of the hammer. The solid line is the force in the pile, and the dotted line is the pile velocity. On the left-hand side, we have the impact of the hammer at the pile top, and on the right-hand side, we have the reflection from the pile bottom. That includes all of the reflections in between the top and the bottom of the pile. During pile driving, this information is obtained under each and every hammer blow. It may take 500, it may take 1,000. In this case, it took 1,813 blows. I'm reading the number at the bottom left-hand side of this table. It took 1,800 blows to drive this pile. Then we can group these blows into blows per meter and show, or per foot, and show the results in graphical form to indicate the whole history of the driving of this pile. This is pile penetration depth. The y-axis is pile penetration depth, and there we see the maximum compression stress on the pile during pile driving, maximum tension stress, stroke of the hammer, energy of the hammer, as well as on the right-hand side, the static load-bearing capacity, shown in the blue line, versus penetration depth, and the blow count in blows per foot or blows per meter versus penetration depth. So now we were able to extract the static load-bearing capacity of the pile versus penetration depth from the total driving resistance that is measured by the sensors. This information can be used to evaluate the entire system, including the hammer, pile, and soil. During pile driving, it is very important to have a handle on the efficiency of the driving system, because the pile driving blow count is not only a function of the resistance of the soil, it is also affected by the efficiency of the hammer. The best way to evaluate the efficiency of the hammer system is by measuring the energy that reaches the pile top. How much do you think is the ratio of energy that the pile top receives as a function of the maximum rated energy of the hammer, percentage-wise? This is a histogram of hundreds of different projects showing the efficiency of the system. In other words, showing the percentage of energy reaching the top of the pile as a function of the rated energy of the hammer. And as we can see in the histogram, it can be anywhere from 10% to 80%. It could be anything. The overall mean is 35%. So the question is, why does it vary so much? And why is it so low on average? That is because it depends on the mechanical efficiency of the hammer, the state of its maintenance condition, and the condition of the cushions that they put inside the hammer to protect it, and the cushion on top of the pile in the case of concrete pile to protect it. Because all of these reasons put together, in addition to the reaction of the soil, the elasticity of the soil, and so on, will play into the efficiency of the system. During pile driving, the pile experiences all types of driving stresses, including compression, tension, torsion, bending, etc. Should there be any damage on the pile during pile driving, that damage sends back wave reflections that are also registered in the data on top of the pile as an early reflection. As we can see in these cases, an early reflection in the data indicates damage in a concrete pile. Similarly, an early reflection in the data showing a damage in the bottom of the steel pile. The stress at the bottom of the pile during pile driving, if we drive a pile to end-bearing resistance, could potentially be twice that on the top of the pile, because the stress on top of the pile is only from the hammer impact. That compression stress from the hammer travels down the pile length. If there's a lot of end-bearing resistance, also in compression, they both add up at the bottom of the pile. So the measured data at the pile top allows for the assessment of the integrity of the pile, an assessment of its integrity condition, whether it's a crack or a complete damage, and the location of that damage along the pile length for each and every hammer blow. So we talked about hammer performance a little bit and pile performance. Now let's talk about the soil resistance performance. Soil resistance and pile static load bearing capacity assessments under the dynamic load of the hammer. When the hammer impacts the top of the pile, it forces the pile into the ground. That movement of the pile activates soil resistance. These soil resistance forces also send back wave reflections. So now we have basically two waves in the pile. A compression wave from the hammer, wave down, and another wave coming up the pile from the soil resistances. From these measurements at the pile top, the PDA registers both waves going down the pile from the hammer and the waves going up the pile from the soil resistance forces. These measurements at the pile top, knowing the wave going down the pile and the measured wave going up the pile, also allow us to establish a reference showing whether we have no resistance like very early driving or whether we have shaft friction resistance along the pile length and how much end bearing resistance we have. We can then use a computer program CapWeb on the data obtained by the PDA by utilizing numerical methods to separate the dynamic resistance from the static resistance. So we have left the static load bearing resistance from the measured data using signal matching techniques. So measurements of the dynamic effect under the impact of the hammer with the PDA, corresponding CapWeb measurements, CapWeb analysis on these measurements allows us to now simulate the static load test result. Remember, we started by saying that the best thing you can do is do a static load test in order to establish this relationship between pile top load and pile top movement under static load. Now we can simulate that. We can simulate a static load test result from these dynamic measurements utilizing the numerical analysis techniques. So how good is that? How does that compare to actual full-scale static load testing? Over the last 50 years, there have been many studies all over the world, many publications, many reports, sponsored agency reports and studies and correlations that show that if the data quality is good, if the analysis is done properly, then one should expect to have excellent correlation between the results of a dynamic load test and that of a full-scale static load test. This is one case that was published by the American Society of Civil Engineers in what's called a Class A prediction, which means that dynamic testing was done by one authority, the static load testing by another, and the results were independently compared by the owner, in this case, the highway department. There's another case as well published in the ASCE that also shows excellent correlation in this case. So there have been many studies. I'm just only showing you two that have been published by the American Society of Civil Engineers. This dynamic testing is typically implemented on project sites by way of a test pile driving program where the engineer selects a number of piles to be driven and dynamically tested, the purpose of which is to establish production piles length for the remainder of the job, establish a pile driving criteria to establish these piles, also to check on the engineer's design assumptions and on the contractor's equipment, means, and methods. This is a standard conventional way of applying dynamic testing on a project for a driven pile job. However, as of lately, alternatively, some projects drive all production piles with 100% dynamic pile testing with the PDA, with or without test piles driving program. This is now the required procedure in at least Florida in the United States, where every project that has pile driving for the State Highway Department must be 100% tested. They found that this procedure optimizes construction efficiency and economy. It makes the job actually go faster and less expensive than otherwise. It also increases engineering reliability. So now if the design engineer knows that each and every pile has been tested and verified for structural integrity and load-bearing capacity, then the engineer should be able to design with much lower factor of safety or much higher fee factor in the LRFD process, making the job much more efficient and much more economical. So we talked about driven piles as an introduction. I know that most of your projects are board piles, but this is how dynamic pile testing started. That was later applied to cast in situ foundations, including board piles. The very first high-rise building in the world was built in Chicago in 1885. That is where deep foundations were first needed to support these high-rise buildings, the skyscrapers. So the high-rise buildings phenomenon started in 1885 in Chicago, utilizing these hand-dug deep foundation. They used to actually send people down all the way down to bedrock and by hand to dig these foundations. To be sure, then the design engineer and everybody involved went down there, down these deep foundations, 50, 70 feet in the ground, 25 meters on the ground. The design engineer would go down there and check and actually hold meetings down in the bottom of these dug piles. Of course, we don't do that anymore. The use of mechanized board piles actually started in Texas in the 1930s as an outgrowth of oil explorations. So when they would take these drills to explore for shallow oils, and they found there's no oil, then they decided to put some steel cage inside that hole, pour concrete in it, and make it into foundation in the 1930s. Then the Texas Highway Department were the very first to utilize that method of deep foundation support for bridges in the 1950s. So if we happen to be lucky enough, as many of you are, and the water table is very low, then the construction is relatively simple. We just drill a hole in the dry, look down it, easy inspection, and then put the steel cage and pour the concrete in there. However, when the water table is high, then we have to employ other means and methods, such as the use of steel casings, temporarily or permanently in place, and or slurry. The purpose of the slurry is to introduce a fluid into the hole that exerts hydrostatic lateral pressure to keep the wall of the hole in place while we construct the drill shaft, so that soil does not fall into the hole as we are constructing the shaft. We know that hydrostatic pressure is equal to the density times depth. We know the depth, which is the depth of the drill shaft or the board pile. So we have to design the slurry with the proper density to provide the required stress, the required pressure against the wall of the hole. So we have to introduce materials into that slurry, into that fluid, including sand, for example. That is why we have to test the slurry to make sure that the sand does not end up at the bottom of the hole, therefore affecting the end-bearing resistance of the drill shaft. Also does not form the materials inside that slurry do not form a mud cake on the side of the wall that will affect the friction, therefore the geotechnical load-bearing capacity of the shaft. So it's very important to exercise the proper sampling and the proper inspection of the slurry during construction. Then we have to introduce a concrete. We do that from the bottom up using this tremie pipe. So it's a very long a funnel-like pipe with a hopper up on top. We put it all the way down to the bottom of the hole, and we put concrete on the hopper, and we lift it up. Of course, it has to always be inside the concrete. We cannot breach it, otherwise we're going to have a problem with the integrity of the shaft. Except that we cannot see down there. So we may be 25, 30, 40 meters on the ground, full of slurry. We can't see what we're doing down there, but we have to make sure that we know where the bottom of the tremie pipe is and where the top of the concrete is, so they're always in relative location, proper relative location. So inspection is extremely important in this case as well. The steel cage have to be designed properly, not only for structural strength, but also to have openings in it to allow for the concrete to move freely into it and outside it to engage under pressure the side resistance of the hole. This looks like a good design. They even doubled up on the reinforcing steel to make sure that the openings are good enough for the concrete to flow. In this case, well, not so much. So concrete will not flow through the steel cage, so we will have a problem in the integrity of this particular board pile. Similarly, the concrete has to be designed properly, not only for structural strength, obviously, but also for workability. It has to be not only strong enough, but workable enough to flow through the reinforcing cage and engage the side of the hole to provide the frictional resistance needed for geotechnical capacity. So in this case, well, it barely made it. In this case, it didn't even make it at all. So one has to also be mindful of the effect of design on construction and ultimately on the performance of these gas in situ deep foundations. So when we drill the hole, we have to perform a series of inspections, including checking for the verticality of the hole, the plumbness of it, Remember, we are drilling a hole, deep into the ground, 25, 30, 40, 50 meters even. It has to be plumb with very tight tolerance of plumb, of verticality, 1%, 2%, maybe a maximum, perhaps 4%. We can't even see down there, but we have to make sure that it's plumb. We also have to make sure that we have a good hole profile. So we have to test for that. Furthermore, we have to evaluate for the bottom cleanliness and competency of the material at the bottom of the hole. All of that before we put the steel cage and before we pour the concrete into that hole to make the drill shaft in place. The shape and verticality are checked with this newest equipment called SHAPE. That is sent down and up the hole, even inside slurry, down and up the hole. It sends signals out and waits for reflections, and it draws out the shape of the hole and the profile of it versus depth and the verticality of it. It also calculates the volume of the hole and shows us the offset between the bottom and the top of the hole. Every one of these components is important. The volume of the hole is important because later on we can compare the volume of the concrete actually used to make this shaft to the volume of the hole when we checked it before we introduced the concrete. The bottom of the hole cleanliness and competency is checked with this newest equipment quantitatively called SQUID, Shaft Quantitative Inspection Device, that basically has three little probes, three little penetrometers that are pushed into the bottom of the hole, and they register the stiffness, the strength of the material, and the thickness of it to make sure that it meets the design requirements. I propose to you that utilizing such quantitative assessments of the bottom of the hole can fundamentally change the design of bore piles by potentially reducing the depth of the rock socket. The reason the depth of the rock socket is so conservative is because of the uncertainty associated with the condition of the bottom of the hole as far as cleanliness and competency. But if that was to be established for each and every one of these holes, then I believe that one can minimize the depth of that rock socket in the design construction of these bore piles. This is the most expensive portion of the construction of the foundation, is drilling through that rock in order to achieve the required rock socket depth. If we can minimize that, that would be ideal. So we do all of the inspections we can, and we pour the concrete, and the constructed shaft may be perfect, cylindrical, the proper size, as designed, as envisioned, or it may be a little bit off. Well, okay, it's off, but yeah, it's good enough maybe. But sometimes it's very bad. So now we have to worry about the integrity of the shaft and assessment of it. There are many factors as to why we may have these issues with the integrity of the shaft, having to do with subsurface conditions, the design. I mentioned the reinforcing cage. I mentioned the concrete. You can also get into other aspects of it. The installation means and methods, the slurry I mentioned, workmanship, I mentioned inspections. So there are many reasons why we may have integrity issues with these cast in situ bore piles, because we're constructing something way out of sight, way underground. The manuals I mentioned have many chapters having to do with the construction, drilling, and casing practices that cause various types of defects. There have been many studies undertaken throughout the United States and worldwide as to how much defects are in these shafts. And I think the general view is that about 1/3, 20 to 50% of all shafts have some kind of an issue, some kind of a defect or a minor fault. The easiest and the most expedient, the least expensive, and I may say the least reliable method to test for integrity is by pit. This technology is about 50 years old. When this technology came into play, it was the only thing around. So it was wonderful. It was great at the time 50 years ago. It has its ASTM standard, D5882, and it basically relies on the measurement of the pile top reaction to low strain impacts on top of the pile and reflections from the pile bottom. So the engineer here is performing this pit testing by hitting the top of the pile with hammer, and by the way, different hammer weights ought to be used for each test. and an accelerometer on top of the pile to measure the motion of the pile top. The data here shows the impact and then the reflection from the pile bottom. So this is good-looking data, good-looking shaft. This, on the other hand, data showing a shaft with a defect because it has an intermediate reflection at 15 meters while the full length of the shaft is 25 meters. So this reflection in the data indicates that something had caused that reflection. From the characteristics of that reflection, we know that's a defect. We can then use signal matching techniques on this spit data in order to quantify as much as possible, given certain conditions, to quantify the amount and location of this defect on this shaft. The equipment that is used worldwide, probably the mostly used worldwide equipment, is the spit equipment available from Pile Dynamics. So we sell pit equipment worldwide, but this equipment, this testing method has many limitations. I will need a whole hour to just go over the limitations, capability and limitations of this method. Needless to say, it has many limitations. It's the oldest and very old legacy technology. Then came the CSL, cross-hole sonic logging testing of drill shafts, that addresses some of the limitations of the pit testing method, but not all of them. In any event, to perform a CSL testing, which is ASTM standard D6760, now we need more equipment. We need to install access tubes, 1.5-inch access tubes into the shaft when we make it. So we have to pre-plan for the test. The number of these access tubes needed is equal to the diameter of the shaft in feet, or 30 centimeters. So for every 30 centimeters of shaft diameter, we need one of these access tubes. 5-foot diameter shaft, 5 access tubes. So we need the access tubes. Then we need a transmitting equipment, transmitting sensor, and a receiving sensor that will be sent into these tubes. We need a depth encoder to know where these sensors are, and we need the CSL computer itself on the job site. And the engineer has to be present, has to be on the job site to perform this test. So this testing is done as follows. We take these access tubes 2 at a time and we scan in between them. By the way, these access tubes must be filled with water at the time of concreting because we want to use the water as a radiator energy during the curing of the concrete. Otherwise, we may have debonding between the access tubes and the concrete and we'll have a problem with the test. That is why we need these tubes to be filled with water. Very critical. Then we send the transmitting device and the receiving device into the opposite tubes and we send signals in between them. We send signals from the sending device, receiving it with the receiving device in the other opposite tube. Should we have good concrete, then the signal is received in good order. If we happen to have bad concrete or a void or some kind of a soil contamination inside the drill shaft at a certain depth between a certain tube pairs, then that defect will tend to delay the reception of the signal, the receipt of the signal, and weaken it. So we'll send signals every 2 inches, every 3 centimeters, for a 100-foot pile. So we're going to have hundreds, if not thousands, of these signals. We can color code them and stack them on top of each other, and that is how the results are typically presented. So the results of scanning between these 2 access tubes versus depth is typically presented in a graph like this. On the upper right-hand side of the plot, you will see the 2 tubes under consideration and the received signal in the red tube. So this is good-looking data versus depth. So the scanning between these 2 tubes looks excellent, good-looking result, good-looking concrete between these 2 tubes along the length of this particular board pile. Again, this test is performed worldwide with equipment available from Pile Dynamics. So on the left-hand side, we have good scan between these 2 tubes. On the middle one, however, between those 2 tubes, we may have an issue in the shaft in the middle because we have a loss of signal in the middle. And another test shows that we have a loss of signal at the bottom. So between those 2 tubes on this shaft, we will have a defect at the bottom, or what's called a soft bottom on this particular drill shaft. So this is basically how the CSL results are generated and how they are typically evaluated. Then all of this data can be put in the 3D tomography program that shows the location of the defects along the length of the shaft inside the steel cage and in the quadrant. How much does it go inside the area of the shaft? That's very important because if the design engineer wants to evaluate a defective shaft, then he or she will know where the defect is, the extent of it. Furthermore, if the contractor wants to drill down to core to fix the shaft, they will know where to go down and how deep. So it's an improvement, it's a much improvement of the PIT method, obviously. However, it has its own limitations as well. The shaft will have to cure sufficiently enough. It may take 4, 5, 6, 7 days to cure for this test procedure to be applied. Meanwhile, the contractor cannot really use these shafts for anything for a week later. Sometimes we may have debonding for various reasons between these little access tubes and the concrete inside the shaft that will produce bad data, therefore bad test results. If we have a steel casing being used to construct this board pile, that will cause issues with the CSL results for the following reason. When we have a steel casing in the shaft, the concrete, when it consolidates under its own weight, you'll often notice that if you go a day or two after the shaft had been cast, you'll see a pool of water on top of the shaft. That is because the concrete had consolidated downwards under its own weight, and the water, not being able to seep sideways because of the presence of the steel casing, will have to go up. It goes up in what's called bleed water channels. These little bleed water channels will affect the CSL signals, but not the integrity or the strength of the concrete in the shaft. So because of all of these reasons, we may have bad CSL results for no reason of the integrity of the shaft. This is a result of a pit test showing a shaft that is 23 feet in this case with good data. We have the impact on the left-hand side and a reflection from the bottom of the shaft at the full length. So the pit result shows good result, good shaft, no problem. However, the same shaft was also tested with CSL method, showing that the bottom few feet of the shaft, there is no concrete. The shaft is very short according to the CSL results, where the pit results showed excellent result. So what's going on here? Why did the two methods give us various opposite conclusions? So the shaft was completely extracted out of the ground. And it was found that, in fact, the shaft length was full. The pit result shows it properly. It did not show, however, the defect at the bottom of the shaft. It only showed the bottom. The CSL result, on the other hand, because of the bullet size, bullet shape bottom to the shaft or the bottom a few feet, there is no connection between the access tubes, therefore the reinforcing cage and the concrete, so there was no signal being sent between the transmitting and receiving access tubes. So that's why the CSL results were shown as they were shown. So you can have conflicting results from this data. So the newest technology in the assessment of the integrity of board piles in place is the thermal integrity profiling, TIP, ASTM standard D7949. This method relies on the measurement of the temperature of the concrete in the drill shaft during curing, because during curing the concrete, the cementation, the hydration process produces heat. So the idea is to measure the temperature of the shaft, which is typically twice that of the surrounding soil. So it's completely distinguishable from the surrounding soil. So measuring the temperature during the curing process, which would be done within the first 24 to 48 hours of casting, depending on the size of the shaft. So for a perfectly shaped shaft, we should have perfectly uniform temperatures. These temperatures are measured by thermal wire that are strung along the longitudinal reinforcing steel bars, and they have every half meter or so a measuring device on them. And the same thing, we need the number of thermal wires attached to the reinforcing cage is equal to the diameter of the shaft in feet. So every 30 centimeter of diameter, we will have one of these wires. So 5-foot diameter shaft will require 5 of these wires. This type of technology have won numerous innovation awards from ASCE, from DFI, from even NASA for the use of temperature readings to evaluate integrity of concrete in place, of drill shaft and deep foundations. So now if we look at this drill shaft and we look at the measuring on the left-hand side using the green line and the measuring on the right-hand side using the red line. If the shaft is completely uniform, no defect, then the temperature versus depth will be completely uniform and equal. A localized defect will produce a localized reduction in temperature, as we see in the red line on the right in the middle of the plot. This is just so if we look at real data, this is a schematic of how it should look like. Real data, this is a 10-foot diameter shaft, 130 feet deep. It has 10 different wires along the circumference versus depth, showing that wire numbers 7, 8, and 9 at 90 feet depth, about 27 meters, has a defect in that corner at that depth in that shaft due to the reduction of temperature, localized reduction of temperature at that location at that depth. Furthermore, if we compare schematically, if we compare the two opposite temperatures along the shaft length, the both pile lengths, and we see that consistently one side is hotter than the other side. That means that the reinforcing cage had shifted inside the concrete, inside the board pile, because the one side of the shaft showing the higher temperature is closer to the middle of the shaft where the temperature is hottest, and the other cooler side is closer to the soil where it's cooler. So therefore, from these temperature measurements with the tip method, we're able to establish the shape of the concrete, so the temperature readings, and the location of the steel inside the concrete body. The testing is done by no need for the engineer to be on the job site. These thermal wires are sent to the job site. The contractor can simply just zip tie these wires along the length of the reinforcing bar and then put the bar in the hole and pour the concrete and go normally about constructing the shaft. No engineer is needed on the job site. The data is sent automatically through the cloud to the office, so the engineer can be monitoring this, or anybody on the job site, inspectors, the engineer, the contractor, anybody can be monitoring this data through the cloud. No need to be on the job site, automatically done. Then we use this math to transform the measurements of temperature into equivalent concrete volume, therefore concrete radius, and location of the steel inside the concrete of the board pile. This is another example of temperature measurements versus depth, and also showing the result in 3D of the concrete shape and the location of the steel inside it. And these are various other results, just to show you examples. This is a case where the shape, remember we can use the shape to establish the profile of the hole and verticality of it. So the shape here, these are the different results of the shape, and at the same time, thermal wire was used for tip testing, and this is the shape of the concrete inside that hole that we got the shape from using the shape equipment, the profile. So they match very good. Of course, the thermal wire will not tell you anything about the verticality, but the shape equipment, the profile of the hole, will tell you its verticality and plumbness. This is data showing a comparison between tip and CSL results. There we see the reduction of temperature at the very bottom, and then correspondingly the CSL results show similarly showing a soft bottom. So there's consistency in the findings between the tip data and the CSL results. This is another case where, this is a case project that has many of these board piles. They use thermal wire on the very first few of the piles, and realizing that they have an issue. There's a fundamental problem with the way they were constructing these shafts that they found out early on using the very first 6 piles that they put in, because they can establish the integrity and therefore see that there's an issue, a systematic issue in the way they were constructing these piles in the ground within the first day or two of installations. Should they have waited for CSL results, waiting a few days or a week, they would have constructed all of these shafts without even knowing they have an issue. And that would have progressed through the entirety of the project. So time is of essence, not only from a technical point of view, but also from a construction point of view. The same technology of thermal integrity wires has also been used on barrettes and diaphragm walls. So comparison between TIP and CSL, TIP is a much more advanced method over CSL with many advantages over the CSL test method. CSL is 35 years old. This TIP method is about 10 years old and still continuing to be developed. Cost considerations between thermal wires and cross-hole sonic logging. And bottom line, it's about equivalent. When you take into consideration all of the aspects, all of the costs of performing either one of these two methods, the bottom line you will find that as many have found worldwide, it's approximately equivalent in cost. This TIP method had been now used and specified in many states in the United States, also in the UK, and Australia, New Zealand, China. Worldwide, it's taken hold now and replacing the PIT and the CSL method, quite frankly. So I talked about the low strain method for assessment of integrity. A small handheld hammer will send a stress wave that may tell us something about the integrity of the drill shaft or the bore pile. Nothing about load bearing capacity. To do that, we have to perform a high strain test. To do that, we need a bigger hammer. We need a big enough hammer to move the shaft against soil resistance, to mobilize resistance in order to calculate or to measure load bearing capacity. For that, we need to have a hammer. So now we have to bring in a drop hammer to perform this test. The weight of the hammer is 2% of the load that we need to test to. So if we're testing for 1,000 tons static load, we need 20-ton hammer. The test can be performed by attaching the gauges to the bore pile itself. This is old technology, should not be used anymore. Alternatively, we should be using the load cell, which is the load cell, instrument source cell that can be put on top of the shaft, and that's how the dynamic test is performed. This is much more improved, much more accurate way to do a dynamic test. This is what is now being recommended. And there's formulas and math and science actually behind how we transform the results of this load cell into equivalent results on the drill shaft measurements themselves. So similarly, as a driven pile, the same technology, we put the sensors on top of the bore pile, we impact it with a drop hammer, and we measure the wave going down the pile, and we measure going up the pile. Except now, these waves include not only soil resistance effects, but also the non-uniform shape of the shape effects. So for that, we need thermal wires. So every bore pile that is static load tested should have thermal wire in it in order to establish the profile of the pile, in order to allow us to transform the readings of the strain measurements and the analysis of the data by knowing the profile of the pile itself, so we can concentrate on the resistance of the soil, because we want to know the shape of the pile. So all of these reflections due to the non-uniform shape are accounted for in the modeling. So the resistance then is concentrated, the wave up is concentrated on the soil resistance effects. That will allow us to establish the static load test simulation at the pile top and the pile bottom. So this is a non-uniform shaft from the tip wire profiling and the result of dynamic load test. Dynamic load testing should typically be performed with a few blows from that impact hammer with low energy, with progressively increasing energy, low to higher energy, and measuring the displacements. So these are simulated static load tests for one dynamic load test utilizing 4 different hammer impacts. So this is a conventional static load test. We need that for top loading. We need it as a reaction. That's how we perform conventional load test. That's why we need all of that dead weight and the expense of it. About 30 years ago, a very famous professor, Professor George Osterberg, came up with the idea that instead of putting that hydraulic jack on top of the bore pile, let's put it inside it. So we call it the O-cell, except that Professor Osterberg passed away and the patent that he had expired. So now we use it as a bidirectional testing. We don't call it O-cell anymore. The only people who call it O-cell are the people who are selling O-cells. Otherwise, worldwide, and also according to ASTM, it's known as a bidirectional testing. So bidirectional testing is performed as follows. We put the load cell at the bottom, we apply load, and we measure the movement upwards and the movement downwards. So we are loading the friction using end bearing as a reaction, and vice versa, loading the end bearing and using the friction as a reaction until we reach maximum value. From that, we can perhaps establish an equivalent simulate pile top loading, load versus displacement at the pile top from the bottom measurements. And depending on what procedure you use, you may have different answers because sometimes you take the elasticity into consideration, sometimes not. So one have to be careful as to what method and the corresponding accuracy of it in doing that transformation from the measurements at the bottom to equivalent pile top. Sometimes we move the location of that load cell in the body of the shaft in order to optimize how much load we can utilize during this procedure. Of course, we can also put strain gauges, as we should, to measure the load in the pile and therefore get the frictional resistance along the pile length. For that, we should also utilize the tip wire in order to establish the profile of the pile that will allow us to transform the measured strain into force and therefore into corresponding frictional load from the resistance of the soil. So whether it's a dynamic load test, a conventional static load test, a bidirectional load test, one should always have this thermal wire in the board pile in order to have the profile of the pile that is absolutely needed and required for the proper analysis of the data of these tests. So with that, I'm almost on time with 1 minute late. I thank you for your time. I hope you have found this presentation interesting and hopefully useful. This is my email address, very easy, mhussein@pile.com. And this is our website, very easy to remember, pile.com. So I will try to answer any questions, Engineer Hamzi, if anybody may have now, if we have time. Otherwise, I'm more than happy to engage in correspondence with anybody who may have any questions or have any comments.
Thank you, Engineer Hussein, for this very interesting presentation. I see also Dr. Marwan with us, and there are indeed many questions. We will try to cover some of them now, if you have time, Engineer Mohammed, and the rest you can thankfully approach Engineer Hussein directly as he provided his email. Please feel free to do so. Or maybe Dr. Marwan, if you want to take part of the question, because I can see there are some questions addressed to you personally.
Thank you, Hamza. Thank you, Engineer Mohammed, for a really informative presentation. And no, Hamza, you can take it forward from your side. Any question will be addressed to me, I will answer it.
Okay, super. And to be honest, Engineer Mohammed, after seeing all these advancement and sophistication in the piling activities, it reminded me to something Professor Mandolini. Recently, I met him and he said he is specializing in piling just to convince people not to use it. So unfortunately, some people are overlooking, some of us as engineers are overlooking the quality assurance and quality control in piling and rely on piling as a magical solution that it will take all the loads and they will never fail. But as you demonstrated, it requires a lot of work to ensure quality assurance. Starting with the questions, I think there is one question asking and addressed to you as well, Dr. Marwan. Driven or precast piles in UAE is not common. Integrity test required also on them. And he want to ask you, Dr. Marwan, if precast piles can be used in UAE.
Yeah, I think the first part, Engineer Hussein could reply to it regarding the precast in the UAE. There is
Pile integrity on the precast, yeah.
Pile integrity in precast for sure it's required, and Engineer Hussein will be giving more details about that. Regarding using it in UAE, the precast, I think there is no any limitation related to that. The only problem is, the location, the impact of hammering or drilling those piles. This is only the limitations. Also, the type of soil, for sure, is also because here, especially in Dubai, we have a little bit hard soil, which we call it Dubai sedimentary rock. There will be the precast is not working. The limitation also for it, it's not carrying a lot of loads because, the transportation and the size of these piles, sometimes here in some towers where we have building loads is very high. We go for 30, 40, 50 meters long piles. So it will be for sure as the precast will be really challenging to do it. From the concept, there is no any problem to use it, but we have to look and to consider our surrounding environment and the impact of using these piles to the surrounding environment. environment. Yes, thank you.
And in fact, driven piles are used offshore, for example, for oil installations all throughout the Arabian Gulf. And they're typically steel pipe piles, and they range in length for maybe more than 1,000 feet, 300 meters or more. And near shore construction, driven piles are also used as well. I know that, for example, the bridge from Saudi Arabia to Bahrain, the old one, is founded on driven piles, precast concrete driven piles. Of course, the use of driven piles on land for typical building structures, that depends on the designer's preference and experience, availability of contractors to do the work, and also the suitability, as Dr. Marwan said, depending on the geotechnical conditions, the loads needed, and also the depth that needs to be used. But as Dr. Marwan also said, fundamentally, there should not be a limitation as far as their technical applicability. It then becomes only a practical aspect of it as to when and where and how it can be applied.
Thank you, Engineer Hussein and Dr. Marwan, for this. And I can confirm also, Engineer Mohammed, as you said, between Bahrain and Saudi, the driven piles were used. And as I'm based sometimes in Bahrain, and we have been seeing driven piles used since the 1960, I believe, 1970. And recently we have been reusing driven piles installed since then, and they were still in good conditions. For some reason, they are not using them anymore or any frequent, but we used also frequently ductile iron driven piles.
Yes, yes.
In the Gulf region, so they are still used in our region. So another question, can you please comment on the reliability of high strain dynamic testing of large diameter open-ended driven steel pipe piles?
That's an excellent question. The hottest topic, at least in the United States right now, in deep foundations, is the large diameter open-ended steel pipe piles. The United States government has undertaken quite an extensive, very expensive effort and research program looking into these large diameter steel pipe piles. There are at least two very large projects that are now starting to get online for large bridge structures that require a lot of ship impact design considerations that will be using large diameter steel pipe piles. I'm talking like 3-meter diameter or more, and maybe 50 meters or more. So the basic issue with the use of steel pipe piles, particularly open-ended steel pipe piles, first of all, large diameter pipe piles cannot be driven closed-ended. Otherwise, they are too much volume, and they cannot be driven due to the elastic response of the pile, of the soil, pile-soil interaction when you have such large volume. So they have to be driven open-ended. Now, when we drive them open-ended, they may or may not plug. It's a problem if they plug, so we have to clean them. It's a process, and so on and so forth. But even when they do not plug, or when we unplug them, the pile-soil interaction between the soil inside and outside the pile, plug or unplug or partially plugged, which means that we have plugged, but it moves. So it's extremely complex. And furthermore, the failure mode under the dynamic loading from a hammer and that under a static loading, the failure mode is different because of the inertia effect of the pile inside the soil. So a short answer is that it's the most complex of all deep foundation issues right now. Of course, they exclusively use worldwide open-ended steel pipe piles for offshore applications. But for that, they have very thick wall, 3-inch, 10-centimeter wall thickness, and they have the means to clean them and so on. But stay tuned, I guess, would be my comment, in that we are still in the process of understanding how to analyze and study, design, test, and even construct these very large diameter open-ended steel pipe piles. If you send me an email, I will send you a link perhaps to the FHWA website that they are dealing with this particular issue.
Thank you, Engineer Hussein, on that. Maybe a note related to that or a question, Engineer Hussein. Do you have any collaboration in this regard with open-ended piles and monopiles offshore with Deltares, for example? Dr. Al-Qadi, I know he's involved in such kind of studies on open-ended piles.
Yes, we perform a lot of testing. Probably the most, let's say, worldwide on these oil platforms, and I know I personally have had cooperations with Mark Randolph in Australia, for example, and Harry Paulson and others, and we have cooperations in West Africa. We of course do a lot, most of the testing for Aramco, for example, for Qatar Gas. For NPCC, for example, in UAE, in the North Sea, in Brazil, and so on. So there's a lot of data. A lot of people are looking into that and trying to optimize these foundations because of cost constraints.
Thank you. Another question, I think, related to the dynamic pilot test when you mention it and compare it to the compression. But this question is asking, what about the tension load test?
Excellent question. If the person who asked, please send an email. I will send to you several papers that we have written on the topic. So here's the deal with that. Although we're doing the dynamic load test in compression, we are able to separate the resistance into skin friction and end bearing. So from that, we take a certain percentage of that skin friction, typically 80% of the compression skin friction, as an uplift capacity. So in the CapWeb program that analyzes the PDA data, we can generate a simulated uplift load versus movement graph from the compression components, from the compression resistance during the test. So yes, it can be done, and the papers I will send you will have correlations between that and actual full-scale static load testing and uplift.
Thank you, Engineer Hussein. Before taking the other questions, there are some non-technical questions like the webinar will be recorded. Yes, it will be recorded, and there will be certificates provided by GRL or BDI. We will send them the list, and hopefully we will arrange for the certificates. And some people, Engineer Hussein, asking if you will share the slides or if you are being able to share the slides.
I will send you a form of that, Engineer Hamza, and you can distribute it as you wish.
Okay, super.
But
Thank you.
please note that these are kind of copyrighted, my slides, so use them with prudence and care.
Okay, sure. Thank you. So continuing with the questions, another question asking all the instruments or gauges we are using for the CABWAB analysis are sacrificial?
No, they are reusable.
Okay.
The gauges are simply attached to the side of the pile by bolting during the test and then taken out and reused again. So they are not sacrificial, they are reusable.
Thank you. Another question, in dynamic pile load test, do the hammer's mass and drop height sufficiently characterize the pile performance, or must we have delved into the waveform analysis considering site and case-specific stress wave propagation, damping of the soil, impedance, and truly validate axial capacity and optimize the design?
Correct. So the hammer is only the energy that is needed to move the pile to activate resistance in order to evaluate load-bearing capacity. So you have to have the hammer of the appropriate size, and you have, I mean by appropriate size is it is related to the impedance of the pile and the resistance of the soil. So the best way I can suggest to you to size the hammer, I gave you a rule of thumb of 2% of the load, static load you're trying to mobilize. However, a better way would be a more accurate and site-specific way is to actually use wave equation simulation analyses in order to size the hammer. Because that way you can put the pile model, you can put the soil resistances, and you can impact it with a certain hammer weight and size and drop height and optimize the hammer. So that way you can simulate before you do the test what you can expect as a result, and therefore to optimize the the setup by minimizing the weight of the hammer, and you have to also put a few inches of plywood to cushion it and so on. So it's a process that can scientifically be done by simulation with wave equation analyses. So when you go on the job site, you are assured that when you perform this dynamic test with the hammer that you have at hand, you have the hammer of the right size, meaning weight and drop height, and you have to have enough movement, sufficient movement, in order to activate the resistance. So typically, these tests are performed as a proof test in order to just show a certain amount of capacity, not necessarily as an ultimate capacity test, because for that, you really need to have a whole lot of displacement, particularly for large size board piles. You may have to move them inches, as you would note under the static load test. But that opens up its own issues, because if you move a shaft 10 centimeters to evaluate its ultimate capacity, do you really still have all of the resistances, or it's only residual resistance that you have after such movement? And would such movement be allowed under the structure from a serviceability point of view? So bottom line is that yes, you can size the hammer appropriately for an easy and reliable proof test. That's no problem.
Thank you, Engineer Hussein. Another question, a hypothetical question, that if the test for verification purposes to be conducted on the same drilled shaft, then which one shall be done first? Is it the static or the dynamic pile load test?
It's another good question, and we have seen it both ways, and I have not seen much difference between them, except that if you perform the static load test first and you move the pile significantly in order to mobilize the maximum resistance, maybe up to the failure load, then you have altered the pile's own interaction characteristics, both in friction and in bearing. Then the dynamic test, maybe afterwards, a little different or maybe better. Depends on how much. I guess the short answer would be it depends. But it should not really make that much of a difference, unless if you perform the dynamic test first and then later on you do the static test, where you move the pile a whole lot during the static test than you did on the dynamic test. Then you may have different mobilization of at least end bearing resistance. So you have to do it thoughtfully. Please send me an email. I will send you a reference to a paper where that was done, and what I have called using superposition of end bearing and skin friction resistance in order to optimize the correspondence or the correlation between dynamic testing and static testing.
Thank you. Another question about the squid equipment. Is there any plan to develop it for smaller diameter piles? And in large diameter piles, should we use more than one squid?
The question to both is yes. There are units now that are smaller in size. If you send me an email, I will send you the literature on that. Smaller in size for smaller size board piles. As far to the next question, we don't have to have different skids, different squids. The same squid is used to test the bottom of the shaft in 5 locations, the 4 coordinates and the middle. So it's very easy. You just pick it up and poke it down in 4 locations and in the middle. It takes about 10 minutes or less.
Thank you. Another question, can we do BIT test on steel pipe? If yes, how to read or interpret the wave?
The answer is no. PIT is only applicable to solid body piles, full piles, a board pile, a precast concrete pile, a concrete filled steel pipe pile, but it has to be full. You cannot test an open-ended steel pipe pile with it, simply because the pit method relies on the one-dimensional, that's a keyword, one-dimensional elastic wave propagation. On an open-ended steel pipe pile, the propagation of the stress wave under the small hammer impact is 3-dimensional. So at least 2-dimensional in the body of the pile itself in the wall. So when you impact the top of the pile and you're measuring the motion on top of the pile next to the impact, you're not really measuring the entire area at once. And that's one reason. The other reason is the ratio of cross-section of the steel to the side area of the body of the pile is so small that the wave will simply dissipate dissipates into the soil, and you'll not have a good reflection from the bottom of the pile at the measuring time. So the short answer is pit is not recommended on open-ended steel pipe piles.
Thank you. Another question, how to decide on the weight of the handheld hammer for the low strain biointegrity test?
Typically, the weight of the hammer basically controls the frequency components of the wave inside the pile. So sometimes you want high frequency, sometimes you need low frequency, and it also controls how far the wave goes inside the pile. So it is typically recommended in the United States, when we perform pit testing, we use 3 different hammer weights. At least 2, I prefer 3, but at least 2 hammer weights. A lighter hammer weight, like let's see, 1 pound will be half a kilogram, and 2 pound will be 1 or 1.5 kilogram. So 2 different hammer weights will give you different components of frequency components and different depth and different width of the impact wave. So that's why it's preferred to do the pit testing with different hammer weights. And also each test should not only be 1 impact, should be 3 or 4 impacts averaged. So each hammer weight will have 3 impacts averaged with the 2 hammer weights. Furthermore, if you have a board pile with larger diameter, you should do the test in the middle and try to do it elsewhere also along the top of the pile, not just one location. So you should really take the time and collect data. I know that in the Gulf area, they do it very quickly, and the data I have seen is only 1 impact at 1 location, and they do it very fast, and it is not good to do it that way. You really should take the time to perform the test properly. Quality is more important than quantity when it comes to testing with the spit testing.
Thank you. And Hussein, another question, can the BIT or the bile integrity test be used to detect soft toe debris in the bile, or what else can be used?
Soft toe is a name given to a pile that either is shorter than designed, or there's not much enough end bearing. Pit testing, if you have a good reflection from the bottom of the pile, may tell you something about that. CSL will tell you more, and the same thing with thermotegel profiling will tell you about the soft toe, because you have the temperature reading at the bottom. So soft toe has 2 implications, a structural integrity aspect to it and a geotechnical load bearing capacity aspect to it. The fundamental end result is that a soft toe will give you less end bearing resistance.
Okay, thank you. Another question about the ASTM, which I have also noticed, to be honest. I believe ASTM, if they don't have any revision for more than 10 years, they will withdraw the standard without replacement. So the question is saying ASTM D6760 is withdrawn without any replacement code. Can we still use it?
Thank you for the question, Engineer Hamza. It has recently been reinstated.
And in case if it is withdrawn, not this specific one, because they have many ASTM standards withdrawn without replacement. In that case,
so typically, when it's withdrawn, there is a note saying that why it has been withdrawn. In many cases, such as was the case on the one you mentioned, it was withdrawn for administrative reasons. So if it's withdrawn for administrative reason, there's no reason why you shouldn't continue to use it, because it's only administration and administrating the issue of that particular standard, but not necessarily a technical problem with it.
Thank you. Another question about the shape equipment. Can it be used inside a partially filled hole with water, or it is either saturated or dry?
There are 2 types of shape. One is for a wet construction, and one is for dry construction. And if you send me an email as well, I will send you the literature on both. You can use the shape for both conditions.
We have so many questions keep coming. I think maybe you want to address it to Engineer Hussein, and hopefully he can find the time to respond to you. It has been over the time already, Engineer Hussein, but the people are still with us. They are still interested in this topic, and thank you for sharing all of these answers and technical details with us. Dr. Marwan, if you are with us, if you want to add anything, or we will close with final words from Engineer Mohammed.
No, well, we just like to thank Engineer Mohammed. You could see a lot of questions. People they are interested to ask more and more, and looking forward to invite you in future occasion here in Dubai or in Geo Virtual or GeoTalk, and you can have your closing remark for the presentation. Yeah.
I would like to close by thanking Dr. Marwan and Engineer Hamza for allowing me the opportunity to present to you today. I thank you so very much, and I very much enjoy being with the GGE. And if anything I can help with at all in any way I possibly can, I would love to do that. Please take care, stay well, and stay in touch.
Thank you, and assalamu alaikum everyone. We'll share the recording as soon as it is ready.
Very good. Wa alaikum salam.